Pablo?
Okay, thank you, Yuval. It is a great pleasure to introduce Enrique to this special seminar. I met Enrique many years ago in the course of Álgebra 1 in the Facultad de Ciencias Exactas y Naturales in Buenos Aires, where I am right now. And we were studying at that time algebra and then other topics. And then when Enrique finished his PhD with Liggett, Thomas Liggett in UCLA, he came to São Paulo, where I was doing a master thesis, and he was my advisor in interacting particle systems. At that point, Enrique told me, read this paper from Liggett, and then I did my PhD thesis with Enrique in this TASEP, simple exclusion process. And then we worked in a couple of other papers, but we were in contact all the time. Enrique is a figure in interacting particle systems, and it is a great pleasure to have the opportunity to present him here. Enrique, gracias.
Okay, thanks to you, and well, thanks to the organizers, and it's my pleasure to speak here. Okay, so I'll be talking about a joint work with Leonardo Rolla from the University of São Paulo. And it's the subject is going to be a variation of the contact process in one dimension. So I'll start with a brief description of the standard contact process, and then I will explain what's the variation we're going to introduce. So in the contact process is a Markov process, and we will work in one dimension, so the state space will be this one. It's a continuous time Markov process, and it somehow represents the spread of an infection or the spread of a population. If you think of in terms of infection, you look, let's call X this space. If eta is in X, then you think of eta of X, X in Z, being equal to 1 if X is infected, and eta of X equals 0 if X is not infected. In terms of a population, you can think of eta of X equal 1 being the presence of an individual at X, and eta of X equals 0 being that the site X is empty. So the evolution of the process depends on a parameter lambda, a positive parameter. And the idea is that at rate lambda, each site that has a 1 will transmit a 1 to each of its neighbors. At rate lambda, it transmits a 1 to the right, and at rate lambda, independently, it transmits a 1 to the left. Now, there's already a 1 in these sites, and nothing happens. And then at rate 1, eta of X equals 0 goes to eta of X equal, eta of X equal 1 goes to eta of X equals 0. So you can think as that at exponential times of parameter 1, a site which is infected recovers from the infection and is no longer infected. Now, what's going to be the small difference of this process with the one I'm going to speak of today is what we call a boundary condition. Suppose that you have a rightmost infected point. Then you will have a different parameter to infect the point which is further to the right. So suppose the infected points are these. Then this will transmit the infection at rate lambda to the left. This will transmit the infection at rate lambda in both directions, and so will this one to the left. So, but we have two parameters. So I'm going to call one of the parameters the internal infection parameter, which is the one we're going to have here. But if this is a leftmost point which is infected, then the infection to the left is transmitted at a different parameter, lambda e. And the same happens here to the right. This is transmitted at rate lambda e. Okay, so the first study of this process with modified boundary conditions is a paper by Duret and Sinasi. Of the year 2000. I'll say in a few minutes what are the main results they have. But before that, I'm going to explain how this process is constructed. Actually, it can be constructed in many ways, but the most useful construction is the graphical construction, which is due to Ted Harris. And in this graphical construction, you think of time of going upwards. Time goes upwards like this. You have a certain line here, which is time 0. Here you have the points of z. And you're going to give, for each site, each point of z, you're going to give a Poisson process of parameter 1 on this line. You'll put some marks, which are death marks, or if you want, recovery marks. In terms of infection, you think at those times, if the individual at this site is infected, then at this time it recovers from the infection. It may be later, might be that later it gets infected again, of course. So you do that on each site. And then you have to say how the infection is transmitted. So for that purpose, you give Poisson processes of parameter lambda going in both directions. And if this point is infected at time 0, then it transmits the infection at this time towards the right. And it might transmit towards the left at another time. So that's when you have just one parameter lambda. If you have both the two parameters, lambda e and lambda I, then you can think of this. You can look at the smaller of these parameters, put arrows according to the Poisson process of that parameter, and then put another Poisson process independent of this one with a parameter which is the difference between the two values. So whether you're going to use the extra marks depends on whether you are on the boundary of the infection region or not. Okay, so this construction then tells you the following. If you want to see if a certain point is infected at a certain time, say this point, is this X infected at this time? Well, you have to look at the infected points in the origin and see if there is a path which moves along the vertical lines, which never crosses on one of these death points, and which might use some of the arrows. So for instance here, if this point was infected at time 0, then this one will be infected at this time here. And then it will recover here. So an open path will be a sequence of vertical lines and arrows, but which doesn't cross x's. So these are the open paths, and those are the paths that transmit the infection. Okay, so in the case where you have the classical contact process, where you have just one parameter lambda, this construction tells you immediately the following: that if one other thing before I say that. We are going to identify this space with subsets of Z in the obvious way. Yeah? That A is identified with the indicator function of A. So if I take a subset of ZA, and I can start the process from A, that means that the points which are infected are exactly the points of A, and the points in the complement are not infected. So one thing that follows immediately from this construction is this. If you have two subsets of Z, and you look at the process, the starting condition is put as an upper index, and you look at this at time t, then if you construct the process starting from A union B, and you construct the process from starting from A and starting from B, and you do them with the same Poisson processes, then this is going to happen. That's immediate because you just have to follow the open path which start at A or at B. Now,
is it true independently of the values of lambda E and lambda I?
No, this was for the case where lambda is fixed and there's only one parameter lambda. So it's important because now that we're going to introduce two parameters, this is no longer true. Now, there's a weaker statement than this one, which says the following. Suppose that A is contained in B. Then the same construction will tell you that this one is contained here. The points which are infected when you start from A are contained in the points that are infected when you start from B. Now, this still will hold if lambda E is less than or equal to lambda I. But it doesn't hold if this is violated. Now, this one doesn't hold whenever the lambdas are different. So if this, you need this for this to be true. But since I'm going to talk about the modified border condition, we will always be in a situation in which this doesn't hold. Now, whether this holds or not depends whether you have this or you don't have it. It's easy to prove that. You can think easily of examples where if this is violated, then this won't be true anymore. Okay. And now anyone who has worked with particle systems knows that the fact that the process is monotone in this sense is a very useful tool. So when this is not true, we have many more difficult to prove whatever result you want to prove than if we do have this condition. Okay. So now I'll state the results which are in the paper by Duret and Sinazi. Okay. No, maybe, yeah. Yeah. Mm-hmm. No, before that, I'll say something else. When you look at the contact process without these new boundary conditions, there is a critical value for lambda. And if lambda is smaller than the critical value, or even equal to the critical value, then the probability of, if you start with a finite number of one infected point, of not being the empty set at time t goes to 0 as t goes to infinity. So in other words, when lambda is less than this critical value, or equal to this critical value, if you start with just one infected point, or even a finite number of points, at some point the infection will disappear. If lambda is bigger than this value, then the probability of eta 0t being different from the empty set does not go to 0. It goes to some constant c, which is positive. Okay. So this is what we call the survival probability, often called theta. Well, okay. Okay, now we're going to start the process from configurations which have infinitely many infected points to the left of the origin, but only a finite number to the right, maybe none at all. So in that case, you have a rightmost infected point. So if eta is among those configurations, I'm going to call R of eta the rightmost infected point. That is the sup of the set of x's such that eta of x is 1. Okay, now let's see what happens if you start from the configuration z minus. Z minus means the set of x's in z which are less than or equal to 0, all the non-positive integers. So you think that all the points, all the sites which are to the left of the origin are infected and all the others are not. Then you want to say what happens to this, the rightmost infected point at time t. Okay, there's an interesting result which is quite old, due to Rick Durrett, which says the following. If you look at this rightmost infected point at time t and you divide this by t, then this converges almost surely to a constant c. Now this constant may be minus infinity. So this is in the interval minus infinity, infinity, but with a possibility of being equal to minus infinity. Now it happens that if this constant is not negative, then the convergence is also in L1. Yeah. And this happens if and only if lambda is greater than the critical value of the contact process. That is, if you're below the critical value, then the infection not only will disappear rather fast to the left at the asymptotic speed infinity. Well, if you are above the critical value, then this asymptotic speed is strictly positive, and at the critical value, the asymptotic speed is 0. So how is this proved for the classical contact process? It's proved thanks to a subadditive ergodic theorem. Where does the subadditivity come from? It comes from this. You are starting from z minus. So at some time t, you will have some infected points, infinitely many, and one of them is going to be the rightmost. But you have to have some, you're going to have some holes here. So if you look at from this point, it's not, everything is not full now. I mean, you have some zeros in the middle. So if you look at what happens in the next time interval, you're starting from a somehow weaker position than when you started from z minus. Think that you're translating, you're looking always from the rightmost point. So if the process is monotone in the sense that, well, I erased it in this sense. What's going to happen is that the increase of the rightmost position from this time to this time is going to be smaller than if you started from all full. So if you restart the process without full at this time, then the rightmost point is going to increase more than what's going to happen if you start from whatever you got at this time, which is random. So if you think of those increases of the rightmost point from time 0 to time t, and then from time 0 to time t plus s, then you're going to have something like this, where this is the increase you have from 0 to t, if you start with all full. This is the increase you have from time t to time s, if at time t you, t plus s here, if you put all full at time t. So this is a subadditivity, and this allows you to use a subadditive ergodic theorem. Okay, since I'm talking about this theorem, a bit of history. The proof of this result was due to Rick Durrett, and it was somehow implicit in his proof that there was some subadditive ergodic theorem behind it, but Rick did not make that explicit. That was made explicit by Liggett, who wrote a subadditive ergodic theorem, which was an improvement of an older subadditive ergodic theorem due to Kingman. This subadditive theorem of Liggett proved to be very useful, not just in the context of the contact process, but also in other situations. Okay, so the question is now: does this still hold for our process? Well, we needed the subadditivity somehow. So, and how are we going to get the subadditivity? Well, we were going to need the process to verify something like that. Otherwise, we won't have the subadditivity. And this is going to be verified only if lambda I is greater than or equal to lambda E. So we lose the subadditivity and this result if this is not true. So most of what I'm going to say today will be under these circumstances. But there's one result which will not be under that hypothesis. Okay. So now we are in a position to state the results which are due to Durrett and Shinasi. Mm-hmm. So call theta of lambda I, lambda E. These are the parameters of which of the process. The probability that starting from just one point infected and at time t, you don't have the empty set for all t. That is the probability of survival of infection. You start with just one point infected, and you ask whether the probability that the infection will remain forever. One thing which seems obvious, but it's not so easy to prove, is that theta is non-decreasing on each of its parameters. Okay, it seems obvious, but there's no trivial proof. But fortunately, that proof is in this paper. So because we have this monotonicity, we can define two critical values. You can define the critical value of lambda I given a value of lambda E and the critical value of the opposite. So I'm going to write them down because we'll be using them. So lambda I star will be the critical value of lambda I given a value of lambda E. And that's going to be the inf of the lambdas such that theta of lambda E is positive. And we also define the critical value for lambda E. This depends on the value of lambda I, and it's the inf of the lambdas such that theta and now lambda I lambda is positive. Okay, with these definitions, I'm going to continue stating the results by Durrett and Shinasi. First is this result, and they also proved a couple of other things, which are these. Oops. So theorem, let's see now, see. No, sorry, no, this is wrong. No, sorry, this is not what I want to say. No. No, yeah, no, it's fine, yeah, it's fine. Yeah. Okay, so what is this saying? This is saying that even if lambda I is very large, the critical value for lambda I doesn't change. It's still the lambda critical we have for the original non-modified Borer process. Well, this is not too surprising because you're just changing the value of lambda in 2 points. You might increase them in 2 points. You might increase them a lot, but what's happening inside the two rightmost and leftmost infected points is just governed by the other parameter lambda I. So if that one is subcritical, you would expect the infection to disappear. So we get this result. And the other result says this, theorem 2. Yeah?
Is the result that lambda I star is smaller or equal than lambda C, or? You're just saying that it's finite.
No. Okay. No. It's this.
Ah, okay.
Yeah. No.
Thank you.
Yeah. Thank you. That is, the fact that lambda I becomes big doesn't modify the critical value of the lambda I. Yeah. Well, the second result tells you what happens when you fix a lambda I. First of all, if lambda I is bigger than 1, then lambda I critical is less than infinity. That is, for lambda I bigger than 1, you have a sufficiently large value of lambda I for which the infection can survive. And the opposite happens if lambda I is less than or equal to 1. So whatever, even if lambda I is less than or equal to 1, even if lambda I is very large, the infection will not survive. Okay, the second result is the easier one to prove. Why? Because if you look at the infected region, say this is the rightmost point and this is the leftmost point which is infected, then at rate which is not bigger than 1, the infection will go 1 step to the right and 1 step to the left. But at rate 1, this infected point will recover, so it will move, the boundary will move to the left of at least 1 unit at rate 1. So if you look at the position of the rightmost point, it's not better than a recurrent random walk. And so the same happens with that. And at some point, the two walks are going to meet and the infection will disappear. So this is easy to prove, but this one is harder. This one requires some renormalization techniques, and I won't talk about that now. So it's in the paper by Duret and Shinazi. Okay. So we're now going to draw a phase diagram according to the two values of lambda I and lambda E. Okay, this results tells you that in this region here, the process will die out. In this region, the two values of lambda bigger than lambda critical, so here we have survival. Now, the question is what happens here. And, well, one would expect to find a curve which goes like this. Now, one of these results is telling you that the curve does approach asymptotically 1. It has to be above 1 because of this result. But because of this, you know it's going to approach 1 somehow here. So this is, but we, in the paper I read in Shinazi, that's about all we can say about the curve. So now I'm going to state our results, the results of our paper with Rolla. So what we prove is that this curve is actually continuous and strictly monotone. It's strictly decreasing. So it goes like that. Okay, so I'll say a few words about how this is proved. And I also will say something about what happens in this region, on this vertical line. So on this vertical line, you have the lambda I, which is equal to lambda critical. And you increase the lambda, the external rate somehow. You put it larger than the critical value. So you're really modifying the parameter of infection only at 2 points. And when you are with the critical value for both parameters, the process dies out. This was a conjecture for a long time, but was finally proved by Besaid, Halt, and Grimmett, and the proof uses dynamic renormalization techniques. Actually, the same proof will show that on this curve, also the process dies out. But what happens here? Well, we have modified very little. Nevertheless, we can prove that the process survives. This is a bit different of what happens if you modify the process as a fixed point. If you modify the process as a fixed point, in the sense you say, well, from the origin, the infection is propagated at a large rate, will the process survive or not? If you would leave all the other infections at rate lambda critical. Well, that's an open question. That's not known. There is a similar result for bound percolation dimension 2. It's a result by Zhang. And this result says this. The critical value for bond percolation dimension 2 is 1/2. So suppose that on percolation, you say that all the bonds are open with probability 1/2 independent of each other, except the bonds on a certain vertical line. And there you put a probability which is bigger than 1/2. Well, Zhang proves that that's not enough to have percolation, in the sense that you won't have infinite open path in this case. So one suspects that if you just modify the value of lambda on one point and you keep the other values at critical value, then probably you won't have the system won't survive, the infection won't survive. But that's not known. So what we do here is a bit different. We are changing the values of lambda, but at some points which depend on which configuration we have. It's a boundary point, and that's different. And actually, there are reasons to believe that that helps more the propagation of infection. Okay.
And when on this line, when the infection survives, do you know how it survives?
And I know a bit. It survives, but the probability of the origin being infected goes to 0 as time goes to infinity.
Okay.
And the process doesn't have an invariant measure, which is not trivial. So it's going to survive like this. Say you start with the origin infected, and then with some positive probability, some points are going to be infected further and further to the right. I believe, but that in fact the origin will be infected again at later times, but the probability of it being infected at time t will go to 0 as time goes to infinity. That second statement is certainly true. It's easy to prove. But
okay, so the probability of being infected should decay like a power, but with an exponent between 0 and 1?
I don't know.
Okay.
Yeah.
You have an upper bound for the how the probability of 0 being infecting decays, or
no? No, maybe. Maybe something has been done for the standard contact process at the critical value, and probably that will be very similar. But I don't know what's exactly what's known about that. Yeah.
Thank you.
Enrique?
Sí.
Would you have an invariant measure as seen from the rightmost particle?
An invariant measure for the system seen from the rightmost particle. Was that the question?
Yeah. Yes.
Well, I'm going to talk about the invariant measure for the process seen from the rightmost particle. So they are old results of Duret already, which say this. If lambda is greater or equal to lambda critical, then the process seen from the rightmost infected point has an invariant measure. So in the case where, in the case we're interested.
No, also the critical case, I didn't remember that. Yes.
Yeah. Okay. So this should be the same, actually. There should be an invariant measure seen from the rightmost point. But we didn't bother to prove that. But most likely the same proof that Duret wrote will work for this. Yeah.
Thanks.
Okay. So. Well. Okay. So now we come to this. Want to show that this is a continuous and decreasing curve, strictly decreasing. So we're going to show two different things. Wait. So we're going to show that each of the critical values of each of the parameters is a strictly monotone function of the other parameter. So when you increase one parameter, the critical value of the other parameter decreases strictly. This shows that the curve does not have horizontal parts nor vertical parts, so it's continuous because it's decreasing. And the fact that it's decreasing follows from the result of Duret and Shinazi. Now, the proofs of these results are different. But if you increase the external rate, then you can show that this critical value decreases. And you can do the same here, but not with the same proof. So both proofs use the asymptotic speed of the system. So remember that we are in this region. So there is an asymptotic speed, because in this region, lambda e is less than lambda I. So we can use the results of the existence of the asymptotic speed. So I'll say a few words now about how these things are proved. One question, what time did I start?
10 past.
10 past, so okay. So I'll try and finish at 05, say. Okay. So I'll start with giving an idea of how this is proved. So this is going to need the existence of an invariant measure, which Pablo asked about, of the process seen from the rightmost point. So you're starting the process, say, from z minus. So at all times, there is a rightmost point. And you're going to look at the process from this point. So you shift your space to putting the origin on that rightmost infected point. And therefore, you can consider that you have a process on 0, 1 to the z minus now. Now, looking at the process here, this process will have an invariant measure mu. Now, this invariant measure has a property, which is that if you look at it from the origin, it's in some sense bigger than if you look what you see from the point -1 towards the left. So oops, yeah. So remember, R of eta is the rightmost point of eta which is infected. This is a soup of the x's such that eta of x is 1. Now we are going to see this phi of eta is going to be eta union R of eta plus 1. That is, you take the set eta, the set of infected points, there's a rightmost point, and you add another point 1 unit to the right. Well, so this is a transformation on your state space. And if you translate it again by 1, you can always think that the rightmost point is the origin. And what happens is that once you've done that, and you do this for a measure mu, you apply the same transformation for the measure mu, measure mu being the invariant measure for the process seen from the rightmost point. It happens that phi of mu is bigger than the translation of mu. Bigger means the following here, means that you can put the two measures on the same probability space. Say that mu is less than nu if, well, I'm going to go in a different definition. If integral of f of eta d mu is less than integral of f of eta d nu for all increasing f. Now, what increasing is increasing in a partial order. We are in a state space where you have a partial order. So suppose f is increasing in the partial order, and then if this happens, you say that mu is less than nu. And what happens if you add a point and you look at the new measure, it's above the old measure, when mu is the invariant measure for the process seen from the rightmost point. So why does this help? Well, this helps because to prove this, you note the following. You're going to start the process from your measure mu, and the process will behave as a standard contact process with just one parameter until the extra parameter, well, no, I'm sorry, no. The process is going to start with parameters lambda I and lambda E. But if you increase the lambda E, at some point, you're going to create a new, an extra point to the right. And this will give you a bigger measure than the one you have before, because up to that point, you were under the invariant measure. So you start with invariant measure, you remain on the invariant measure until the effect of increasing lambda E kicks in. When that kicks in, you get a bigger measure. And besides getting a bigger measure, you have moved the rightmost point one further unit to the right. So, you're pushing the rightmost point to the right, and you are increasing your measure. So since the process is monotone, this you can keep on doing this, and each time the extra value for lambda E kicks in, you get an extra unit and you increase your measure. So that gives you times at which you are increasing the rightmost point, And these occur at according to a Poisson process of a certain fixed parameter. So your rightmost point moves to the right faster. So in other words, alpha of lambda I, lambda E plus epsilon is going to be strictly bigger than alpha of lambda E, lambda epsilon, lambda I, lambda E. Okay, if epsilon is greater than 0. Now, since you have so this will allow you to prove one of the two results here. And you will also need to finish the proof, you will need this and the fact that at criticality, the asymptotic speed is 0. So alpha of lambda I, lambda E star of lambda I is 0. When you fix the parameter lambda I, take this lambda I at its critical value according to this lambda I, then the asymptotic speed is 0. Okay, this is not easy to prove, but I'll come back to that. And the same happens for the other one. You fix your lambda E, and then you take lambda I star of lambda E. And this is also 0. Okay, a few words about the proof of this. It's similar to the proof that it's done for the standard contact process, which tells you that alpha of lambda critical is 0. The proof is quite involved. It requires renormalization, and it's quite cumbersome to write. But the idea is that if alpha is positive, then that means asymptotic speed is positive, and you can move around certain parallelograms with open paths, and this with a slope alpha. Now, if you take these parallelograms with slope alpha big enough, then the probability of having an open path along this parallelogram goes to 1. And then you can slightly reduce the value of lambda in such a way that this still happens with high probability, and use that to prove that the system survives. So if this alpha is positive, then you can reduce the parameters of the infection and still be on a be supercritical. You still have a positive probability of survival. Okay, so using this and that, you get which result? Well, you get this. It's strictly, well, if you increase lambda E, then the lambda I star decreases. Now, to prove this one, you will need something similar. You would need to show that if you increase the lambda I, then the alpha also increases. This is a bit harder to prove, and it took us longer to prove that. The proof is shorter to write, but it's somehow more complicated. And it uses the following. Mm-hmm. Yeah. Okay, take a set A. Take a new set A prime, which is A union X, where X is to the right of A. So X is bigger than the rightmost point of A. Then you can show the following, that the expectation of the rightmost point of when you start with A prime at time t is bigger than the expectation of the rightmost point of when you start with A plus some constant t theta star, where theta star is positive and theta star is actually the probability of survival of a certain process, which I'll describe now. Theta star is a probability of survival of a process zeta t, where this process has also two parameters, lambda I and lambda e, but the lambda e only intervenes for the rightmost point on the rightmost point. So the leftmost point infects at rate lambda I on both directions, but the rightmost point infects to the right with parameter lambda e. Then it's easy to show that if this is taken as a critical value for that lambda I, this process does survive. And the reason is that if lambda I is fixed and is bigger than lambda critical, we're always in that situation, then it doesn't matter too much what you put here, because towards the left, you're always going to use lambda I. So the process will survive. You can think of this. Even if this was a critical value for lambda I, then the asymptotic speed to the right is 0, but the asymptotic speed to the left is like if you had lambda I alone, because it's this lambda I does not intervene to the left. So you have an asymptotic speed which is negative here. So in this region, the process will have a positive probability of survival, because here you always have lambda I, and lambda I is supercritical. So this theta star is positive. So the point is to prove this. This requires a rather unusual coupling. And this unusual coupling consists in doing the following. Here you have the extra point x, this one. Here you have the points of A. Well, you're going to look at what happens with this point. This point will have a certain number, a certain open path where the infection is transmitted. And you're going to construct the process starting from A alone, by putting exactly the same path here. So the process starting from A, you put here these paths, exactly the same ones, translated. You repeat that. And now, if this doesn't die out, then, and this won't die out, but this one will always be some unit to the right of this one. And if this one dies out, then this one will die out too. But the fact that the extra points you have are further away to the left here than from here means that the fact that these are dying out does not affect you so much here than it does here. So given that this one dies out, the process here has a more positive behavior than the process here, because it's not affected as badly as it is here. This is, you see, if this path comes here, you know it's going to die out. But here it's going to be easier because you're much nearer to this point. So that's what you use to prove this. And this is essential to finally prove the second result. And that gives you this, this monotonicity and continuity of that function. Okay, so now I won't. So now the proof of the last result. The last result is the one that says that here you have a positive probability of survival. Well, this is quite involved, and the reason it's involved is that you lose the monotonicity here. This has created, we initially had a proof that wasn't quite correct, and then we had to amend it, and it took us quite a while. The proof again uses this fact here, this idea here, that if you have a point to the right that dies out, and your other points are further away, the fact that this one dies out does not affect you so negatively than if it is closer to these points. Okay, so now finally I'll state two open problems. Well, the first open problem, I have already mentioned it. What happens if you just modify lambda at some point? That is, you say the infection starting from the origin is bigger than lambda critical, and all the other infections are at the critical value. So I suspect the process dies out, but that seems hard to prove, and we don't know how to do it. And the other thing, which is probably easier, but haven't thought much about it, but it's not trivial, is there an asymptotic speed when the process has lost its monotonicity? That is, if you take lambda e greater than lambda I, well, so as I said, the process is no longer monotone, so you can't use directly the Savaric-Vergodic theorem. Can you prove, nevertheless, that R of eta t z minus over t converges almost surely to some constant? I presume this is right, and this shouldn't be so difficult, but I don't have a proof. Okay, thanks.
Let's take Enrique. Is there any question?
Ora.
So there was
Nobody's asking? Okay, so I have a question. Enrique, you know that there is a speed if you have an invariant method, right?
Wait, say it again. I missed something.
Since you have an invariant measure as seen from the rightmost particle, you know that there is speed.
Yeah. Yes.
But your problem is that you don't know how to show that you converge to that speed, right?
Well, no, but the thing that you have that asymptotic speed is true even if you don't start with invariant measure, except on the critical, for the critical value. That is, if lambda is bigger than lambda critical,
yes,
the asymptotic speed will always be the same whatever semi-infinite initial configuration you start with.
Okay.
Now, when the lambda is equal to lambda critical, and now you know that the asymptotic speed is 0, well, this is no longer true. That is, the asymptotic speed exists if you start with all full, and it's the same if you start with your invariant measure, but not if you start from an arbitrary configuration.
Okay, thank you. The other question is about the configuration at the origin.
Oh, it freezes.
Yes, my question is about why do you think, okay, why is it so different, this thing about, why do you think that the process survives when you have a bonus on the boundary and not when you have a bonus on a fixed point?
Well, that it survives when you have a bonus on the boundary, this we know. It's,
yes.
Well, okay, now, why I don't think it's the same when you have, okay. I think the best way to look at that is looking at it's very heuristic what I'm going to say. I think it's the right reason. Look at what's called the contour. When you think, for instance, in percolation, when you don't have percolation, you have a contour of the region that you can reach from the origin. Well, in terms of a contact process, you also have contours. They are harder to write down because you're in continuous time and so on. But it can be done. And actually, one old paper of Griffith uses this contour idea to give a bound for the critical value. Now, just okay. So you're looking at the infection starting from what point? Suppose the infection does all this. Then the contour should be something like that. If it dies out, you have a contour like this. Now, how much is it that you have to pay? You have to pay each time you would like the process to move to the right here and break this contour. But this will be the bigger value, the bigger value of lambda E. And you will have to somehow overcome this bigger value of lambda E many times on this contour. Well, if you just have the extra value here and you look at a reasonable contour, well, it might do something like that, but you won't have to beat the extra value of lambda E many times. You shouldn't expect that to happen. I mean, you don't have a proof, but I think that's the idea.
Thank you. So it's not. So it will die even for absurdly large values of lambda. Well, okay, I don't know if lambda is the right word, but even if you take lambda 0 very, very large.
Yeah, I think you will still die out. By the way, Zhang's proofs for bond percolation in 2 dimensions works for on the vertical line around the origin. You can put a p as close to 1 as you want, and still you don't have percolation.
I had another question. So you know that you have survival when lambda E is larger than lambda I. You know that when lambda E is equal to let's say that lambda I is equal to lambda C.
Lambda I.
You're on this vertical line.
Okay,
here.
On this line, yeah.
So you know that on the upper part of the line you have survival.
Yeah.
You know that on the here you have. Well, you don't have survival, but you have 0 speed.
Here.
Yeah. Yes.
Yeah, right.
Below, do you know whether
the speed is minus infinity below.
As the speed is minus infinity.
Yeah.
Okay.
Wait, no.
That was my question.
When both values are less than lambda critical, the speed is minus.
Yes. So here, do you know if the speed is negative or minus?
Here.
Yeah.
So you say lambda I is equal to lambda critical, and lambda E is less than lambda critical.
Yeah. So
I would expect the speed to be negative, but
negative but finite. Okay.
Yeah, I would expect that.
Okay.
Yeah.
But
didn't think about that. But
okay.
That's what I would expect. Yeah.
And when the speed is minus infinite, like so what's at what rate do you go to?
That I don't know.
Okay.
It's minus infinity, but well, if both values are less than lambda critical, I would expect you go to minus infinity very fast, actually. Exponentially fast, maybe. Yeah. Now, one other thing, since we're talking about this boundary, looking at the process from the rightmost point, we know what happens in the supercritical case. You converge to, seeing from the process from that point, you converge to the invariant measure, the mu invariant measure, and the same happens at the critical value. Now, what happens below the critical value? And well, it is known that you do converge to something, but you converge to something which is finite. That is, you start with Z minus, and you are subcritical. This is the standard contact process, so just one parameter lambda. You're below the critical value. So you start with C minus, so at all times you have a rightmost infected point. And the measure you see from that point, that rightmost infected point, does converge to a measure which concentrates on finite configurations. And those finite configurations are the quasi-stationary measure of the process.
Pablo's back.
Okay. Thank you very much. Any other question there? Okay, let's thanks Enrique again.
I have a question. Is it possible?
Ah.
Yeah. Okay. So what about CLT for the rightmost particle?
What?
CLT.
Okay. A central limit theorem,
Yeah.
say. Well, okay, that's known in the supercritical case. It's a result by Galvez and Presutti that tells you that the position does behave to a central limit theorem. Now, besides the proof of Galvez and Presutti, there's a new proof, well, new, it's not new now, but it was new at the time it came, of Kuksek, which is very nice proof. And he wrote it for oriented percolation, but basically the same proof for the contact process. So yeah, you do have a central limit theorem in the supercritical case, at least.
Okay, thank you.
Can I make just a quick comment? Can you hear me? My camera is broken. Can you hear me?
Yeah.
Yes.
Yes, yes.
Yeah, sorry for my camera being broken. So Celio, who is also in the meeting, he's been reading the preprint and he's been thinking about it. And it seems he knows how to come up with the proof for the invariant measure seen from the rightmost infected site. Definitely when the lambda I is supercritical, and now he's checking if that also works when lambda I is critical, and that you have an invariant measure and that it is unique, so that you have ergodicities. So you do have an asymptotic speed, and moreover, it's not random. But not being random depends on the invariant measure being unique. But it's still preliminary. It's a very, very recent. And just since Pablo has been asking, I thought I would share. And if it all works, it allows to answer the observation by Hubert, which is very interesting. That you have negative speed but finite. Mm-hmm. Usually, either you have zero speed because you're critical, or you have positive speed because you're supercritical, or you die very quickly. You die exponentially fast, which means the rightmost site, the position of the rightmost infected site goes exponentially fast to minus infinity. And it is somehow interesting that we have a model that is not percolating, but the speed is negative but finite, because mm-hmm. you are somehow bulky to the left of the border. Just a comment, since the questions have been asked. Sorry for my not having the camera.
No, thanks for the observation.
You can see Celio. He's a student at UFMG. You can see him in the camera. He does have a working camera.
Okay. Okay. Yeah. Good.
Okay, so thank you, Enrique. I leave the chair with Hubert.
Okay, so thank you very much, Enrique. And yes, I guess we can all thank Enrique again.